In this video, we're going to talk about using what are called formal circuit methods that are needed to solve circuits that you can't use the series and parallel rules on. All the circuits we've seen to date using voltage divider and current divider are all you need to really solve circuits, and that applies in a vast majority of the cases, but there are a few that you can't. They have a bit different structure, and I'll show you an example of one in just a second. So instead of going back to the VI relations, KVL and KCL, and solving a load of equations, we're going to develop something called the node method, which very efficiently uses the VI relations, KVL and KCL. Turns out it's so efficient that you may want to use it to check your answers that you get by other techniques. It's very nice and very general. One of the surprises is that you can use the node method to prove that circuits conserve power. The assumptions underlying that proof are pretty interesting, and we'll see how that works out. But first, a circuit that's a little harder than it looks. So here's a circuit, and let's look at its structure to see if it fits into the mold of series and parallel circuits. Well, let's start over here. This resistor looks like it could be in parallel with this series combination, but these two aren't in series because there's this branch going off into that 2 ohm resistor. So these aren't in series, and because of that branch, this is not in parallel with those two either. And these two look sort of be in series, but they're not because of this side branch, etc. If you go through it, nothing is in series with anything, and nothing is in parallel with anything. It's kind of interesting. We still want to solve circuits like this, and we can do it. We know that given the VI relations, KVL and KCL, we can solve any circuit. It's just that it's very tedious to solve it that way because, let's see, this circuit has 1, 2, 3, 4, 5, 6 elements. That means 12 unknowns. And I don't really want to write all those equations, all 12 equations in 12 unknowns. So let's talk about the node method. The node method is very easy and very simple. So here's our circuit. And what you do is you start by defining what are called node voltages. You pick a node as a reference, and usually it's the one that you don't write KCL for if you use the old techniques. There's usually this big node at the bottom, and I'm going to pick it as being the reference. And that symbol means the reference. And I have defined node voltages at almost all the other nodes. So here's a node here, a node here, and a node there. And what these voltages E1 means is the voltage between that node and the reference. E2 means the voltage between this node and the reference. And since the voltage source is attached to this node and the reference, we know that this node voltage is Vn, so I don't need to define a node voltage there. It's not necessary. However, something a little bit more interesting, that when we define node voltages, it also means it doesn't matter which path we took to go between this node and the reference. That is the voltage there. So that's saying that this voltage is equal to that voltage plus that voltage. So you could go around this way, or you could go around that way to get to that reference, and that voltage is E1. Well, that implies KVL. So we're using the KVL relations implicitly when we define node voltages as just being the voltage between some point in the circuit, a node, and the reference. And this voltage applies no matter what path you take to get between the two. So The n minus 1 here refers to the fact that we don't need to write define a node voltage for the reference. It's the reference. And it turns out in this case we don't need to write 3 node voltages. This is a 4-node circuit because we already know one of the node voltages. So we only need to define 2, E1 and E2. That is going to turn out to be our only set of unknowns. We don't need anything else. So that means we only need 2 equations to write those 2 unknowns. We've used KVL. So the next thing we're going to do is use KCL at each node, and we're going to write the KCL equations using the node voltages and the VI relations all at once. So that uses up all the things, tools that we need. We know that the defining node voltages uses up KVL. We're going to write KCL, use up the VI relations while we do it. So how do we do that? So here's the set of KCL equations for this circuit. So let's start with E1. The node here, node 1, there's a current going that way, current going that way, and a current going that way. And I'm going to write the KCL equation that all those currents sum to 0. But as I write the currents, I'm going to go ahead and use the VI relations. Now the current going that way means plus to minus that way. And so that is E1 minus Vn is that voltage divided by 1, which is the resistance. So that's what I mean by using the VI relations at the same time. So the west going current is E1 minus Vn over 1. The south going current is simply E1 over 1. And the east going current is E1 minus E2 divided by 1 again. And those have to be 0. That's KCL at that node. So we can write KCL at the other node where E2 is. So it's E2 minus E1 divided by 1, E2 divided by 1, and E2 minus Vn divided by 2 is the last KCL equations. So we've used up all the circuit laws. There are KVL, KCL, and the VI relations. Turns out they're all implicitly or explicitly used. We have wound up with 2 equations and 2 unknowns, and all you have to do is solve them, and there's no tricks to solving them. You just solve this set of linear equations. Now I want to point out something that also makes the node method almost foolproof. And that is that if you look at the equations for node 1, since we did sum of currents leaving, the node voltage for that node always appears with a plus sign. The node voltage at the other nodes always appears with a minus sign. Always, 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 if you obey this convention. So you can see that happens here too. E2 is always with a plus sign, and the other node voltages are always there with a minus sign. And so at least you get the signs right for the voltages when you write the KCL equations. You got to be careful and use the right value for the resistance. Other than that, it's foolproof, and hopefully you can solve the equations without error. So 2 equations, 2 unknowns, and all we have to do is just solve them for the node voltages. And I did this. You should check to make sure I got the right answers, in that E1 is going to be 6/13 of Vn. It just turns out to be 6/13. No good reason why it should be, but it is. And E2 is 5/13. So just solve 2 equations, 2 unknowns, and you get the result in terms of Vn. And now what you do is you express the output in terms of the node voltage. And for this circuit example, I chose that current as being my output. And I think it's pretty easy to see that that's just E2 divided by 1. And so the answer is 5/13 Vn. A little note about units here. This current should be in amperes, and it looks like I have a voltage here, and I do, but it turns out the 5/13, if you look back up at this answer, it turns out to have no dimensions, but that 1 has a dimension of ohms. When you get numeric answers like this, it tends to hide the fact that the units are correct. It may look a little strange, but if you did everything correctly, the units should all work out and your answer would be correct. Okay, let's use the node method to prove that all circuits conserve power. Very powerful statement. So, here is a section of a generic circuit. I'm not going to tell you, and I don't even know what these elements are. They're just elements. And it's a piece of a circuit because I7 is going somewhere, 5, 6, and 4. They're going off. There's some elements that have those numbers, and I don't need to define exactly what the circuit is because I want a very general answer. I'm using this core of the circuit to illustrate the point I want to make. Now, what I'm headed for is to show that the VK IK is equal to 0. So what I'm going to do is express the voltages across each element in terms of node voltages. The direction for that voltage is going to be defined by the direction I chose for the currents. So I3 is going that way, so I'm going to define V3 to be that, so that I get a consistent answer that goes according to the rules by which we define VI relations. So voltage across here goes like that, and the voltage across there is going to be like that. Okay? So here's what we're going to do. We're going to write VK IK for each element using the node voltages. Okay? So let's look at element 1. Let's see, I1 goes that way, that means it's plus to minus that way, so that means it's EB minus EA. That's what I wrote there. V2, let's see, plus to minus that way, node C minus node A, right, okay, times I2, and EC minus EB times I3, that looks right. And let's see, for circuit element 5, which is somewhere out here, is EB minus whatever's at the end of it times I5, and the same thing for I6. I didn't write I4 and I7. We won't need them. Okay, so the next thing I want to do is, because I'm considering the sum of all these terms, which are now expressed in terms of node voltages, I want to group them according to node. What I'm going to do is group these equations according to EB. I'm going to find all the terms involving EB and write them down, collect them together. So the EB terms, we have EB times these currents. So let's check our answers here. We have an I1 from this equation. There's no EB in this equation. Here's a minus I3, okay. EB times an I5, okay. And an EB times an I6. Okay, yeah, we got them all. Okay. Notice that this equation is the KCL equation for node B. So I1, I is leaving, I3 is entering, so it gets a minus sign, I5 is leaving, I6 is leaving. So that is KCL. And what's going to happen when you group the sum of the VKs, IKs, you group them according to node voltage, what you're going to get is that KCL, because KCL applies at every node, you're going to get a KCL equation. So what since all these terms are 0, for every node voltage, the sum of the VK-IKs is 0. Amazing. So we have proven what we wanted. That this is summed over all elements in a circuit, including sources, that the VK-IKs, multiply them together, add them up, you get 0. Okay, so that proves that all circuits conserve power. But what did we use to prove this? What we used were the node voltages, and then when we group terms, we use KCL. Using node voltages implies KVL. So, turns out the only thing that was required to prove that circuits conserve power is KVL and KCL. What that means, the VI relations are immaterial. So this proves that for circuits consisting of resistors, inductors, capacitors, nonlinear elements like diodes, all kinds of things, it really doesn't matter. It's just that KVL and KCL are sufficient to show that circuits conserve power. That's really interesting, I think. It really is a very interesting and important result that all circuits conserve power, no matter how you build them, and no matter what elements are used to construct them. Okay, so it turns out you can use the node method for circuits involving impedances. So, and that's because complex amplitudes obey KVL and KCL. And so you can use the node method for an RLC circuit. So I took the simple circuit we used in our example and I replaced some elements by some inductors and capacitors. So again, using the convention that capital letters denote complex amplitudes, the node voltages are now complex amplitudes. That's a capital V, even though it may not look like it. You define a reference, and you do exactly what we did before. Here are the two KCL equations for nodes 1 and node 2. And now, instead of resistance, you're dividing by the impedance. So let's see, E1 minus Vn, well, that's this voltage. And the impedance of the inductor is 1 times S. I'm using S instead of J2 pi F again because it really cleans up the notation in the equations. And I'll substitute that back in when I'm done. E1 is sitting on top of the capacitor, so it's E1 divided by the impedance of the 1 farad capacitor, and E1 minus E2 divided by the resistance of the 1 ohm resistor, etc. So you should check the equations and make sure I didn't make an error. And of course the final step is to express the output, which is that current, in terms of node voltages, and in this case it's E2 divided by the impedance of the inductor, which is 1S. Okay, so everything follows. So you can solve any circuit using the node method, whether it's just resistors or whether it's RLC circuits, it really doesn't matter. You can solve all of them. And similarly, because it works, the proof that we just used to prove conservation of power applies also to complex power, because that's the complex power. And this is the average power for the kth element that also applies. The reason is that if you have the KCL equations, and if you just take the conjugates of them, that's what can be, the conjugates also, adding up the conjugates of complex amplitudes of current also equals 0. So this shows that power in all senses that we've talked about, complex amplitudes or power in the time domain, all have to add up to be 0. All circuits from any viewpoint satisfy conservation of power. All right, so the node method, we can solve any RL circuit using it, and it's especially used when voltage and current divider shortcuts can't be applied. As we start talking about electronics, you'll see there's a really good reason why we need to talk about the node method. And like I said, it can be used to check your answers. It's so easy to use and so efficient, it's hard to write down the wrong node, the wrong KCL equations. So it's a pretty good way of checking answers. And it's because of the generality of the node method. It applies to all circuits. It's the underlying reason we could use it to prove that circuits conserve power.